Okay, I better start because the red light has gone on. So, yeah, today's lecture is going to be quite probably easy to digest, and probably the next lecture will also be quite easy to digest. We're introducing some concepts and terminologies so that we can then go along and describe our solids with the more accurate electron band theory. So remember yesterday we were starting to describe some types of bonding in solids. This bond here is called the covalent bond, and it's defined by electron sharing. So the electrons are shared from the two atoms that are in close proximity, rather than the ionic bonding. Remember when one atom transferred a part of its electron or a whole electron to the other atom. In this case, they do sharing. And there's a very wide range of materials that are covalently bonded. Most of them, or I should say, be careful, very many of the semiconductor materials have covalent bonds. So here we have a structure of diamond. This is a very common structure here. It's a diamond structure. This is the conventional cell here. Along the bottom, it forms like a zigzag here, a zigzag across the top there. And it's very much like a face-centered cubic, which we'll get to in a moment. If you can just imagine a cubic cell with the atoms at the corners of a square. And the face-centered cubic is where on all of the faces of the square, there is also an atom. So on the front face, there's an atom there. On the side, there's an atom. On the top, there's an atom. Okay, so you can think of this diamond structure, which is also called zinc blende structure, which we'll see just shortly. Well, the zinc blende is where you've got two types of atoms rather than just one, but it has the same structure. So you can think of it as being like the face-centered cubic, and in addition, you've just got this atom here, which goes from the atom here at the origin, if you like, quarter, 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 and then there's another one over here, and then two more up here. So that's a good way of sort of remembering what the diamond structure looks like. Now, in these materials, we have, for example, diamond, which has our carbon atoms. It has the electronic configuration given by, in brackets here, we have helium. This is just so we don't need to write out all the electrons, okay? Helium is 1s occupied by 2 electrons, so we just put it there. And the valence electrons of the diamond or the carbon atom, 2s2, that means 2 electrons are occupied in the s orbital, and 2p, 2 electrons are in the p orbital. Now the s orbitals can hold 2 electrons, the p electrons can hold 6. So this outermost p orbital is lacking 4 electrons. And so what it does is it shares with its neighbor, and so it can fill these outermost electron orbitals. And it does that by forming what are called sp hybrid orbitals, and they are depicted here, or if you like here. This is what they look like. So this might be the center of your carbon atom, and there is orbitals reaching out to the next carbon atom here, one here and one here. You can see it has a tetragonal local environment. So this is what the orbital of s electrons look like. You have your 3p orbitals, each of which can hold 2 electrons. Okay, you have px along the x-axis, py along the y-axis, and pz. And so they hybridize the s and the p to form these so-called sp orbitals. Very sort of important and common kind of bonding configuration. And this kind of covalent sp bonding also occurs in, if you like, the methane atom, where you've got a carbon atom in the middle and 4 hydrogen atoms. we also have this kind of tetrahedral environment. And so the carbon atom, as I mentioned before, it's lacking the p electrons can hold 6 electrons, and we have 2 are already occupied by the carbon atom. So the carbon atom is seeking 4 more electrons, which it can get from each hydrogen atom. Okay, so hydrogen's got 1 electron, and another one here, another one here. So they contribute the 4 electrons that the carbon is wanting to become very stable. Okay, so this is a very stable and happy molecule. So as I mentioned before, this is a kind of bonding configuration that is in very many semiconductors. What other semiconductors? Right here, it's almost ubiquitous, which means it's like everywhere. Diamond, silicon has it, germanium, and this other important group of semiconductor materials are called the 3,5 materials. Why? Because one of the species comes from the 3 column in the periodic table, and the other one comes from the column 5 in the periodic table. And these are very important semiconductor materials for, device engineering and electronic components. Gallium arsenide, aluminium arsenide, indium phosphide, and also a different family created by the 2,6 group of atoms, cadmium sulfide, cadmium telluride, and so on. Again, they exhibit this kind of bonding arrangement. And of course, they've got 2 species, so instead of them all being the same color, this might be gallium, and this might be your nitrogen, and so on. And then this is called the zinc blende structure. Okay, probably one should mention that it's not exactly purely covalent bonding. I mean, when you actually get down and analyze the detailed electronic structure of these materials, you might find some component of the bonding is ionic. Small part might be ionic, and some part might be covalent. And, there's a lot of work, sort of arguing about what kind of bonding goes on in some particular material, new material. And there's certain ways that you can analyze and classify, but it's only a name. It's really only semantics, okay? But these are the names that we need to learn. Okay, another interesting and important one is so-called sp2 bonding, and you form hybrid bonds with the s kind of orbitals and the p electrons, but only 2 of the p orbitals. And in that way, you can create 3 kind of sp2 type of orbitals. And when they're centered on an atom, in the middle here, they have 3 kind of lobes that will reach out. And if you have another atom here of the same kind, you can see that these orbitals will overlap nicely and share the electrons and form strong bonds. So you can see that these kind of bonds are flat bonds, and separated by 120. So it kind of gives you some clue as to what material, for example, might exhibit these kind of bonds. And that is, for example, graphite or graphene, where graphene, as you know, is just a single layer of graphite. In graphite, the layers are held very weakly together with the van der Waals force, and they exhibit this kind of sp2 type bonding there in the plane. And there was 1 electron left over, if you remember from what I showed you. That electron sits up in the pz direction and sort of just sits up there, and it makes these materials very good conductors. Okay, so when it's arranged in graphite or even graphene, as we saw at the start, they are conductor. Whereas diamond, you arrange the carbon atoms in a different way, and it's a semiconductor. Also, these nanotubes, they also exhibit this kind of sp2-like bonding, and as we saw at the start, depending on how they are rolled up, sort of you can imagine changing the angle and then roll it. You can, get conductors or not conductors, sort of metallic nanotubes. Also, you can have nanotubes, so-called multi-walled nanotubes, where you might have a nanotube in a nanotube in a nanotube, or something like that. Also, buckyballs exhibit this kind of sp3 bonding. You can see it's got these three kind of planar type bonds there. And as I mentioned before, you can stack these, make a solid of buckyballs, and when you do that, this becomes an insulator. Okay, so just a little bit more about covalent type bonding. The actual cohesive energy, remember the cohesive energy was, well, you can think of it two ways. You can think of it as the energy, you've got your atoms isolated, and they have a certain energy when you add up the energy of those atoms, and that energy difference from when you bring it together to make the solid. Or alternatively, you might start with the solid and work out the energy to pull all of the atoms apart. So that's, remember, the cohesive energy, and the magnitude of it is similar to ionic bonding. So covalent bonds are strong bonds, and ionic bonds are also strong bonds. And we'll have a look at what energy they are later on. Covalent bonds are characterized by being very directional. So as we saw before, these sp3 or sp2 bonds are very sort of directional in space. Okay, so let's come back now to metallic bonding. So sort of, you would think the most simple kind of bonding perhaps, but it's actually, not so simple. So this table here is the periodic table, okay, and there's two shaded regions which are indicated here as being metals or non-metals, okay. I just put here the boundaries can be disputed because depending how you classify, depending how, but roughly these are accepted as being metals and these white ones non-metals. So what's the point? The point is that you can see that the metals cover a large part of the periodic table, okay, so large part. So they're very important elements, really. Okay, now within the metals, there's kind of three categories that are normally discussed. You have your simple metals, which might be, for example, like sodium, aluminium, potassium, magnesium. Then you have the transition metals that have got your d electrons, your f electrons. And then you have the noble metals, which might be like gold, silver, palladium, where you have filled d bands. And these noble metals are regarded as being unreactive. So you think of your gold ring, okay? It doesn't what do you call it, corrode or tarnish. What I just put in green there is the transition metals, which incorporates the noble metals as well. So, here you have your palladium, nickel. Actually, in this table, you can see that the silver and gold has been actually left out. And, okay, that's because in some cases, they actually act like a simple metal because, as I said before, the d metal is fully occupied, so it doesn't really get involved in the bonding. Okay, so first of all, let's look at simple metals. We did already look a little bit at the sodium ion, remember, in relation to sodium chloride, but now we're just considering bulk metal sodium. So this is kind of, yes, it's a simple metal, and it has, okay, here I've put you the electronic configuration of sodium. So sodium Na has the electronic configuration of neon, okay, which is a noble gas. And then it's just got this one valence electron, which I've indicated here. Yeah, there's obviously something more missing over here. What is that? Yeah. Okay, so it's just got one electron here, and so this electron actually can wander off and become delocalized, you know, in the so-called sort of electron sea, if you like. So when you look at a very simple picture of a sodium bulk, you might see sodium ions and then these free electron sort of sea around them. And yeah, the cohesive energies are in the EV range, but they are not as high as the transition metal cohesive energies. What are some more characteristics of the simple metal bonding? As I said before, the cohesive energies are smaller than ionic crystals and covalent crystals. There's a parameter called the ionic radii. It's sort of a qualitative measure for each kind of element when they are in a particular solid. So for it kind of basically indicates how big, if you like, the atom is. So for sodium, when it's in its metal form, it has a large ionic radii, 3.82 angstrom, which is basically very similar to the lattice spacing of your bulk sodium. Okay, so the electron stays, it goes away a bit from the ion core, but it sort of stays around it and makes it kind of fat, okay, if you like. But when you put it in sodium chloride, okay, this electron was basically given over to the chlorine atom, and then the effective size of the sodium that has lost that electron, its ionic radius becomes 1.98, so much smaller, okay, because it's lost that electron to the chlorine. Simple metal bonding is known to have, it's not directional, it's all sort of smooth in the three-dimensional space, largely. And for these kind of materials, close pack arrangement is preferred, which is not the diamond structure that we saw earlier. That's kind of a more open structure. So the close packed configurations we'll have a little look at. They're like so-called face-centered cubic structure, or the hexagonal close packed structure. We'll get to those shortly. A lot of simple metals form in those kind of structures. Okay, I just said that in words. That's not necessary for me to go in. Yes, okay. Yeah, here's a point. Remember when we had the ionic bonding, we could kind of understand why the material formed, why it was favorable to form, because we could describe the bonding, even though we had to pay to ionize these sodium atoms, we gained energy due to the attraction between the positive and negative charges, okay? But if you think about for the sodium, we only have sodium ions, okay, next door to each other. So you may think, well, why is this favorable? We've got repulsion from these ion cores. But we do know they are still embedded in an average of one electron. This valence electron is still lurking around. So that obviously results in an attraction, an energy gain for the system. So that's why I mean it's not so straightforward to understand as the ionic bonding. Okay, so one way to understand qualitatively why the metallic bonding might be favorable is when we look here at the Schrödinger equation, where basically this term here, the kinetic energy term, where we have here the momentum operator, okay, and we have here the Heisenberg uncertainty principle. So basically this here, the kinetic energy, is proportional to the negative of the average curvature of the wave function, because it's a second derivative, okay, it gives you the curvature. You can think of the wave function just as some, I don't know, however it is in the solid. There's lots of different wave functions depending on what energy and which momentum you are at. But this basically reflects the curvature of the wave function. So what's the point? Okay, here, if you have a material where there's less localization, what does that mean? That means where the orbitals are not so close to the atom, okay? Where they can spread out more, like in a metal. This becomes larger, the displacement, and so you get a smaller variation in your momentum, which will give you a smaller kinetic energy term. So, resulting in a favourable structure. So this is sort of one way of thinking about how delocalization that you have in a metal can be an attractive property. Okay, let's look at transition metals now. Transition metals being the green section here. Okay, here I've just put 4s and 3d electrons have very similar energy. That's just by the wayside. The 4s electrons from your 4d transition metals are fairly delocalized. This here is the 3d row, okay, scandium, titanium, vanadium, chromium. These are the 3ds, and these here are the 4ds, okay, 5ds, 6ds, and so on. So, as I mentioned before, the transition metals are characterized by having strong binding energy or cohesive energy. And as I mentioned before, we also have gold, the noble metal here. And so you can see that gold, where its electronic structure has its 5d electrons all filled up. Okay, so these 5d electrons do not participate in the bonding very much. I wouldn't say, actually, when you're actually studying these things, you do need to, they do play some role, but not like in the other transition metals where the d states are partially filled. So let's just consider a typical transition metal, if you like, ruthenium. Where's ruthenium? That's a 4d here. And its electronic structure is given by that of krypton, which is, okay, this one here. And then we just come along here, filling up the, increasing the number of electrons. And you can see the 4d has only 7 electrons occupied. So this d state is, if you like, short of 3 electrons, and so it's very ready to make bonds with other atoms in its vicinity. It's much more reactive. And in fact, these transition metals, because of this being reactive, are very good, catalysts. In fact, ruthenium is one of the most efficient catalysts for carbon monoxide oxidation. And there are other, they're usually transition metals. But they're expensive, so if you're trying to make catalysts, there's a big effort now to try and make catalysts with the same properties as these transition metals, but made with more abundant kinds of atoms. Okay, so let's come to the next kind of bonding. This is kind of what is called hydrogen bonding, if you like. What kind of systems does hydrogen bonding occur in? Molecular solids. This means room temperature. So some of these kind of materials aren't stable at room temperature. They're only stable at lower temperature because the bonding is so weak. Ice, plastic, DNA, these kind of things. Hydrogen bonding is the main kind of bonding and extremely important. So what does it look like? This is the usual example given here. Basically, it's dipole-dipole kind of interaction involving the hydrogen atoms. The hydrogen atoms are also tiny, right? So they can't actually, their orbitals can't really reach out and overlap with other atoms. So the way they bond is through the dipole moment that they create. Okay, for example, this is a water molecule, and it has a permanent dipole. Why does it have a dipole? Well, you look at your oxygen, oxygen 1s2, that's all filled. The 2s states are filled in the 3p orbitals. You know, p electrons can hold 6 electrons. It's only got 4, so it really wants 2 more electrons to be stable. And so these 2 hydrogen atoms, which just have 1 electron each, bind with the oxygen very readily. So the oxygen has its filled 3p orbital, so very stable. So, but because of this kind of bonding here, the hydrogen atom becomes positively charged, a bit like, you know, in the ionic crystal that we discussed, although hydrogen bonding is a kind of bonding all on its own, just due to the very tiny size of the hydrogen atom. And so the oxygen atom gets some kind of extra negative charge. This delta just means some kind of charge, and it's negative. I don't know what the actual value is. But you can see this will give you a dipole, okay? Negative here, positive here, you will get a dipole moment, okay? So it's directional. So, for example, if you put a lot of these together, water molecules here, they will orientate themselves. See, each one has oxygen, which is negative, and hydrogen, which is positive. They will orientate themselves so that we have the attraction between the positive and the negative at every opportunity. Okay? Okay, I think this is the last type of one, is the van der Waals bonding. So let's have a look at that. This kind of bonding has a number of different names, I guess, depending on what discipline you're in. Or even within the same discipline, it can have a number of names. Fluctuating dipole forces, it can also be called, or dispersion forces, or sometimes, which I haven't actually heard of, molecular bonding. It's maybe that's used in chemistry. But what is the point? The point is that any kind of atoms will exhibit some kind of van der Waals interaction between them. For example, if you look at the hydrogen atom here, the electrons, you know, are orbiting around, if you like that picture, and on average, they may have zero dipole moment because they're moving around, they're fluctuating. But at some point, there will be a momentary dipole moment created, if you like here. Here is be positive, and if both the electrons are over here, that will give rise to a very small dipole moment, here positive to negative, and we can call that P1, this momentary dipole moment. Now, if there is another atom in the vicinity of that, it will experience or feel this electric field here, and it will reorientate its own dipole moment in response to this small electric field. And we'll get to that on the next slide, and we can call that induced dipole moment P2. And these dipole moments, P2 and P1, will interact with each other, and because they're oppositely orientated, there will be an attraction between them. So here I've put the expression for the electric field generated by this little dipole moment P1. And if we want to think about can we think about a dipole moment P can be thought of as the charge, Q, multiplied by the effective distance, if you like. So that's what an electric dipole is. It's due to charge displaced, if you like, and the distance from where that little extra charge is positive and where it's negative. Okay, so I think that's helpful in being able to just think about what is this dipole, electric dipole. So, you know, if we have now two of these helium atoms close to each other, we had the first one, and it will induce an electric field. This one will feel it. It will reorientate itself to set up a little dipole in the opposite direction, P2. And okay, how can we write P2? This is another important thing. The dipole moment can also be written as something called polarizability times the electric field. Okay, so this P2 that was set up in the second atom is equal to the polarizability times this electric field that it felt from the first atom. Little aside, what is polarizability? How can you think about it? It's basically the ability of an atom to form instantaneous dipoles. How readily can it change itself to set up dipoles? And it's a property of, the particular atom. And so from before we had the expression for electric field. Remember, it was 1 over r cubed. So you get 2 of these 1 over r cubes with the polarizability in. And this is ambiguous here. What I'm saying is you end up with an expression that's proportional to 1 over r to the 6, where r is the distance between these dipoles. Okay? Up here should be negative. Okay? And this is a proportionality sign, but it actually, unfortunately, looks like the polarizability. Okay? So all I'm doing is multiplying 1 on r cubed by 1 on r cubed and showing you that it's proportional to minus here, put a minus here, 1 over r to the power 6. And this is, your famous, van der Waals interaction term. 1 over r to the 6, it's very, very well known. Okay, should make a note of that. Okay. And I just want to say, this is another aside, but up until maybe, 5 years ago, these kind of van der Waals interactions were not being taken into account when people were doing very state-of-the-art calculations, but recently this kind of theory has been built into the very state-of-the-art description of solids, and now people can study much more accurately systems that exhibit or depend upon an accurate calculation of the van der Waals force. I can show you some papers maybe later on towards the end of the course, just for fun. Okay, so now we want to look at, this sort of reflects the melting point here as a function of the cohesive energy. Okay, it's kind of on a weird scale here, a bit of a log scale, and so this is temperature in Kelvin. And so the very lowest melting point temperatures are these rare gas or noble gases. Okay, these are the neon, argon, krypton, xenon that have already very filled shells. They're very happy, they're very stable, they don't need to bond with anybody else. So their cohesive energy is very small and they have a very low melting temperature. Then come the simple metals with cohesive energies of, here we have our sodium. What else? We've got rubidium, potassium. These are the alkali metals with just one s electron in their outer shell. The simple metals here have a cohesive energy in the range, 1 to 2. And then we have the noble metals. Remember the higher atomic number materials with d electrons, but they're all filled, so they can't bond as strongly. The noble metals, here we have gold. Okay, what else we've got? Silver. And there's also, some sprinkling and smearing of the different elements. It's not so clear-cut, but we can see here that they have the next highest cohesive energy. And the materials with the very highest melting temperature are these transition metals. In particular, you can see tungsten. up here with the highest cohesive energy and melting temperature. So that's quite a nice way of looking at the materials. All right, so I've just got a summary here of the kinds of bonding that you've been introduced to and that you'll need to know here. We've got the 5 types of bonding: ionic, metallic, covalent, hydrogen bond, van der Waals bonds. Okay, as I said before, like in reality, things are not so clear-cut. It's usually some kind of mixture between types of bonding that you'll have in reality. Just made a little sketch here. This is, I think it's from Ashcroft and Merman here. This is a crystal of argon here. So this is basically van der Waals interactions here. Here we have ionic bonding, where we've got potassium chloride. Okay, before we had sodium chloride, but potassium behaves the same way as sodium here. You've got basically, the electrostatic attractive interaction here. You have the metallic bonding in pure bulk metal here, where the electrons are regarded as a sea of electrons that can readily move around, embedded with the positive ion cores here. And finally, we have this, covalent bonding here, where the very strong and directional bonds are formed between them. Okay, this here's a nice table. That's actually from the textbook that I recommended online that you can get, the Oxford Simple Basic Introduction to Solid State Physics. And it just tabulates these nicely for you. It gives you the types of bonding, a little description, and then some examples and some associated properties that these particular materials have. So it'd be good, for you to have a read of that. Okay. So we've got a little bit of time. So I think I'll just start off the next little bit that we have to do, which is some definitions. Okay, we know the types of materials qualitatively that we are going to deal with, and now we want to sort of set up a sort of framework for studying them. Okay, so we're going to define quite a few things in this topic, which we probably won't get finished today, but we're not meant to finish today, so that's fine. Okay, so what we're going to do is look at Bravais lattice, unit cell, primitive cell, conventional cell, basis, Wigner-Seitz cell, and some common crystal structures. So these are kind of probably what we'll get through right now, just defining what do they mean. Okay, up here I've put the very first thing, 3 ways you may like to think about the crystal lattice. What do we mean? The crystal lattice is also called a Bravais lattice. Okay, so all of these points represent your atoms. Okay, so let's just look at the 3 kinds of ways you can think about it. Okay, you can think of it as an infinite set of points defined by integer sums of a set of linearly independent primitive lattice vectors, which is a bit of a mouthful, or you can think of it as an infinite set of vectors where the addition of 2 will always give you a third that's in the set, or you can think of it as a set of points where the environment at any given point, okay, is going to be exactly the same as if you were at any other point. This shows in 2 dimensions how we kind of set up things. We define some big R lattice vector, okay, subscript mn, which are just integers, and so any lattice point R can be expressed in terms of the primitive vectors A1 and A2. Okay, so here if you start your origin on this atom here, A1 will take you here, A2 is defined here. So any combination of M and N will land you, on another atom. Okay? And then, of course, you do that in 3 dimensions because we have a 3-dimensional solid. In some textbooks, you'll probably find that they don't use A1 and A2. They may use something else. And they may not use M and N as their integers. They'll probably use something else. It just depends. So in 3 dimensions, you just have another lattice vector A3. Okay? So this is what we may have had before. And then now, for real crystal, we need, A3 is defined out here. Okay, we call O here. This is a very simple cubic system, which we are starting off with. Okay, so let us define the unit cell, or the primitive cell. There's a slight difference here, okay? A unit cell is a region of space such that when many of the same unit cells are stacked, we basically generate that complete structure. Okay, there's no gaps in space, it completely fills. It's basically the repeated motif that you repeat throughout all space to get your structure. Okay? So what's the difference between a unit cell and primitive cell? The primitive cell sort of gives you a clue. Primitive, it's the unit cell containing only one single lattice point. Okay? Just one. That's the primitive unit cell. So what do they look like? Let's have a look. They are not unique. This shows a 2-dimensional square lattice, okay? And all of these here, the red or the yellow or even this weird shape here, can be a primitive cell of this lattice. The only criteria, remember, is that when it's repeated, it tessellates. It covers the whole space. So it doesn't matter, how you choose it. It's primitive because it's just got one lattice point. Okay? It's only one lattice, because it's got to share with this one here. So there's not 4 lattice points, there's only one. Okay? Non-primitive unit cell might be this big one here. You can see that it's twice as big, so it doesn't have one lattice point, it's got 2. Same thing here, this has also got 2 instead of 1. These are non-primitive unit cells. Okay. Let's think about this here. Yeah, why I showed this is just so that it's easy for you to see that it's just shifted slightly, like the red one was up here. If you just shift it slightly, you can see that there is actually only one point in the unit cell, even though you may have thought, quickly that there were 4. You just shift them slightly, and you can see that there's only one point in your cell. Okay, and these have got 2, and these have got 2. Okay, the next important definition is a so-called Wigner-Seitz cell. So what is a Wigner-Seitz cell? It's a special choice of primitive cell. Okay, so it's still only got one lattice point, but it is a region of points. It's closer to that particular lattice point than any other lattice point. So basically, the lattice point usually sits in the center of it. So these, what I showed you before, were actually Wigner-Seitz cell. So this is an easy way to remember it. It's a region of points closer to a given lattice point than to any other lattice. Okay, obviously here it's at the border between this one and this one, isn't it? But in here, it's definitely closer to this one. And there's a particular way we can create the Wigner-Seitz cell, which I'll show you right now. I'll show you over here. But first of all, let's just look at what we have got so far. This was a primitive, so now we've got some kind of hexagonal lattice, okay? So this would be a primitive cell, an example of one, okay? You can see it's just got one lattice point in that cell, okay? There's something also called a conventional cell, which is important for you to know. Conventional cell is a unit cell, but it's not the primitive one. But it may be more convenient sometimes to use a conventional cell. Remember that zinc blende or the diamond structure that we had? It was a nice square, and inside it had a lot of atoms. Well, we could use that square cell as the conventional cell and work with that for all of our calculations. It's more convenient than having these sort of non-orthogonal axes. For example, a conventional cell on this lattice, we could choose it to be like this, nice and orthogonal, and it's just got two atoms in the unit cell. So that's what a conventional cell means. Primitive, you know, and the Wigner-Seitz is a primitive cell, but where the region in that Wigner-Seitz cell is closest to the lattice point that it contains. So how do you create it? This shape looks a little bit, you know, you may think, oh, I'm not sure how I'd create that, but there's rules to create it. So what you do, first of all, is you draw a straight line. Well, if you like, you can start on your atom of choice. Draw lines to the nearest neighbors, okay? And then one by one, you draw a perpendicular bisector, okay? So you get the green line, and then you look at the next, the distance between this and this atom, draw a perpendicular line. Okay, and you can see that it's going to enclose a unique area. Here, the line, the perpendicular bisected of this line gets you this line here, and then finally we'll consider this distance here, and you'll get the other corner of the Wigner-Seitz cell. Okay, so if you've got some complicated crystal and you're not sure what the Wigner-Seitz cell looks like, you can always, at least in 2 dimensions, it's easy to draw it. The next thing I want to highlight is that it may seem surprising, but the number of possible Bravais lattices of fundamentally different symmetry in 2-dimensional is limited to 5. Okay, it's only 5, and these are them here. Okay, we've got the simple square lattice, we've got a rectangular lattice, we have got what is called a centered rectangular lattice. Here we've got a hexagonal lattice and some oblique rectangular lattice where you've got some variable angle here, and these are not equal to each other. And in 3 dimensions, there are only 4. Okay, and have I given you the 3-dimensional ones? I probably haven't given you the 3-dimensional ones, but you can easily look those up, and you don't need to know them. But there's only 14, and in Chapter 7 of Ashcroft and Merman, yeah, it shows you all of the other 14 for the 3-dimensional space. Okay, so these are very, these are the only 5 lattices. The ones that, you know, normally people deal with, you know, are the square. So hexagonal is very common. If you have a complicated material, yes, you can get these much more difficult structures that you have to look at. So, okay, it's 5-2, and I think I'm just going to leave it here rather than starting off on the next section. So we'll just leave it here for now, and on Friday we'll continue, yeah, with this lecture. Okay.